On January 2nd, 3I Atlas was recorded as being associated with an unusual X-ray emission phenomenon appearing in the region of space between the Sun and the Earth. At the same time, 3I Atlas continued to execute intermittent changes in its trajectory, while emitting mysterious energy pulses in the form of X-rays and ultraviolet radiation. What has particularly puzzled the scientific community is the clear imbalance between the small size of 3I Atlas and the powerful non-gravitational thrust it produces. According to current physical models, an object of this scale should not be able to sustain such high levels of energetic activity without structural failure. However, 3I Atlas has instead demonstrated an unusual stability, showing no signs of fragmentation despite repeated exposure to thermal and mechanical stress. The growing contradiction between observational data and theoretical models has pushed 3I Atlas beyond the familiar explanatory framework of orbital mechanics and cometary physics. Although experts have not reached any conclusion regarding the possibility of artificial intelligence, they acknowledge that existing mathematical models cannot fully describe the mechanisms of self-organization and complex motion that 3I Atlas is exhibiting. It is this unresolved tension that has transformed 3I Atlas into one of the most significant space mysteries of the present moment, rendering all predictions about its journey toward Jupiter in 2026 increasingly uncertain. These mysteries are what we will explore together next. On December 19th, the passage of 3 Atlas past Earth unfolded as a moment designed for confirmation rather than surprise, because the closest approach had been calculated long in advance and carried no element of danger. The distance of approximately 270 million kilometers placed 3 Atlas well outside any zone of gravitational instability, yet close enough for telescopes to refine measurements of position velocity and brightness with exceptional clarity. For observers on Earth, the flyby of 3 Atlas was expected to serve as a final validation point, where prediction and reality would briefly overlap before the object continued outward. During the hours surrounding closest approach, tracking systems across multiple observatories reported that 3 Atlas behaved exactly as the equations required. The measured position of 3 Atlas matched the projected path, and the velocity vectors aligned within margins so small that they reinforced confidence rather than uncertainty. Nothing about the immediate motion of 3 Atlas suggested instability deviation or the presence of unaccounted forces. This apparent normality was significant because a close flyby amplifies any hidden discrepancies that might exist within orbital models. If 3I Atlas had carried unseen mass experienced asymmetric forces or interacted unexpectedly with Earth's gravity, those effects would have appeared most clearly during this passage. Instead, the flyby of 3I Atlas passed quietly, reinforcing the belief that the object remained governed by gravity alone. As Earth receded behind it, 3 Atlas continued along its projected exit trajectory, and the expectation was that future tracking would simply confirm the same curve extending outward into interstellar space. At that moment, 3 Atlas appeared to complete its role as a cooperative subject, offering no resistance to interpretation and no challenge to established theory. Only later would scientists realize that the calm of December 19th did not represent stability, but rather the final moment before the predictive structure surrounding 3 Atlas began to loosen in subtle but consequential ways. In the days following the December 19th flyby, the first signs of divergence appeared not as dramatic shifts, but as small discrepancies embedded within newly refined tracking data. When astronomers updated the position and velocity measurements of 3I Atlas, the numbers no longer collapsed neatly onto the predicted hyperbolic curve that had defined its motion up to that point. At first, these differences were subtle enough to resemble ordinary measurement noise, the kind that usually disappears as additional data is added to the model. However, as more observations were incorporated, the uncertainty surrounding 3 Atlas began to behave in an unfamiliar way. Instead of narrowing with time, the region of possible future positions expanded, transforming what had been a thin, well-defined line into a widening geometric volume. For 3 Atlas, the future was no longer a precise destination, but a growing cone of probability extending outward into space. This transformation carried deep implications because orbital mechanics relies on uncertainty shrinking as observations accumulate. In standard cases, additional data constrains motion, more tightly reducing ambiguity rather than amplifying it. With 3 at less, the opposite was occurring as each new measurement increased the range of plausible trajectories rather than refining them. The emergence of this uncertainty cone signaled that 3 at last was no longer behaving as a passive object, influenced solely by gravity. Something was introducing variability into the motion of 3 at last, causing small deviations to compound instead of cancel. These deviations did not scatter randomly, but aligned along preferred directions, suggesting a structured influence rather than chaotic disturbance. As the predictive framework stretched and thinned, scientists were forced to confront an unsettling shift in perspective. 3 at last was no longer a point moving along a known path, but a moving source of uncertainty actively reshaping its own forecast. What had once been a straight mathematical promise now opened into a cone whose boundaries could no longer be drawn with confidence. The expanding uncertainty surrounding 3 at soon demanded an explanation that went beyond statistical error, because the deviations observed could not be reconciled with gravity alone. When analysts isolated the motion of 3 at from all known gravitational influences, a residual acceleration remained small in absolute magnitude, yet persistent enough to alter the long-term trajectory. This residual force placed 3 at into a category known as non-gravitational acceleration, a phenomenon familiar in cometary science, but rare in interstellar visitors. The data showed that the velocity of 3 at was changing in ways that standard celestial mechanics could not predict even after accounting for the Sun, the planets, and relativistic corrections. Tracking solutions that once converged now required additional force terms to remain mathematically stable, and those terms could not be derived from gravity. For 3 at, this meant that motion was being shaped by something intrinsic rather than external. Non-gravitational acceleration is usually associated with mass loss, where material escaping from a surface produces a small but measurable thrust. In familiar comets, this process results in smooth, continuous deviations that can be modelled once the rate of outgassing is understood. With 3 at, the acceleration did not behave smoothly, and the direction of the inferred force shifted over time instead of remaining fixed. These deviations were not large enough to suggest violent propulsion, yet they were strong enough to disrupt predictive models that depend on cumulative precision. Each small change in the motion of 3 at altered future calculations, causing uncertainty to grow rather than resolve. The path of 3 at therefore became sensitive to forces that could not be averaged away or treated as background noise. As researchers compared successive datasets, a pattern began to emerge in the way the acceleration appeared and disappeared. The motion of 3 at suggested episodes of influence rather than a constant push, implying that whatever force was acting did so intermittently. This realization marked a shift from treating 3 at as a passive body to considering it as an object whose internal processes actively shaped its journey. At this point in the analysis, the deviation of 3 at no longer represented a correction to an equation, but a doorway into a deeper question about how interstellar matter can behave once it enters the solar system. As the non-gravitational component of motion became clearer, the most unsettling feature of 3 at was not the existence of acceleration itself, but the way that acceleration arrived. Instead of a steady drift that could be smoothed into a continuous curve, the trajectory of 3 at began to resemble a sequence of discrete adjustments. 3 at would appear to follow the expected path for a time, and then the tracking solution would abruptly shift as though the object had taken a step sideways in the mathematical landscape. These changes were described as step-like because the velocity vector of 3 at did not evolve gradually but moved in increments. In one interval, the predicted and observed positions of 3 at would remain consistent, and then a new set of measurements would force a refit that required an additional impulse. When this happened repeatedly, the emerging picture was not of a single deviation, but of multiple deviations separated by periods of relative stability. For familiar cometary outgassing, such behaviour is difficult to produce because thermal processes usually change smoothly as sunlight warms a rotating surface. Jets of gas do not normally switch on and off like a binary signal unless specific internal conditions are capable of storing pressure and releasing it in bursts. If 3 at were behaving like a geyser in vacuum, then 3 at would require a crust strong enough to confine gas, a reservoir capable of building pressure, and a repeated cycle that could sustain impulsive releases. The step-like pattern therefore introduced a question of mechanism, because the shape of the data matters as much as its magnitude. A constant force produces a predictable curve, but an intermittent force produces jaggedness, and 3At was beginning to look jagged in the language of orbital solutions. Each step, even if only meters per second, accumulated into a meaningful divergence over millions of kilometers. What made this more challenging was the apparent regularity of the steps, because randomness would have suggested noise while repetition suggested process. 3At was not merely drifting, and 3At was not merely being perturbed, but 3At was behaving as if something inside it was periodically changing the balance of forces acting upon it. In this stepwise motion, 3At began to feel less like a comet, and more like an unresolved system, one that had not yet revealed the rules behind its rhythm. As the step-like deviations accumulated, the geometry of prediction around 3At changed, in a way that could no longer be described as a technical inconvenience. Instead of a single future path extending outward, analysts were forced to describe the motion of 3At as a spreading volume of possibilities that widened with every new episode of acceleration. This volume was not abstract but mathematically defined, representing all locations where 3At could plausibly be found if the pattern of impulses continued. In classical orbital analysis, uncertainty behaves like a tightening knot because additional observations constrain motion and collapse ambiguity. With 3At, uncertainty behaved in reverse, because each new data point introduced additional divergence rather than resolution. The future of 3At therefore became less predictable with time, even as observational precision improved. This expanding cone of uncertainty was shaped by the timing and direction of the episodic accelerations, which meant that prediction now depended on events that had not yet occurred. To forecast the position of 3At weeks or months ahead, one would need to know not only its current state, but also when the next impulse would occur and in which direction it would act. Because those impulses were not predictable, the cone continued to open. As a result, long-term trajectory estimates for 3At lost their practical meaning. Short-term tracking could still locate 3At with confidence, but beyond a limited horizon, the future path dissolved into a fan of branching outcomes. This was not a failure of measurement, but a reflection of a system whose behavior could not be reduced to initial conditions alone. The widening cone carried important implications for understanding the past as well as the future. If 3At had been undergoing similar episodic accelerations before detection, then attempts to trace its origin backward through space would inherit the same uncertainty. Every unseen impulse would shift the inferred source region, stretching the past into its own cone of ambiguity. In this way, 3At became temporally elusive because both its future destination and its past origin were blurred by the same mechanism. The object could still be observed, still be measured, and still be described, yet it resisted being placed cleanly within a single narrative of motion. What emerged was not chaos, but a structured indeterminacy, where 3At followed rules that had not yet been written into the language of celestial mechanics. As attention shifted from motion to emission, the brightness of 3At revealed a rhythm that was too regular to ignore and too persistent to dismiss as noise. Photometric observations showed that the light reflected and emitted by 3At did not fluctuate randomly, but rose and fell in repeating patterns that could be measured across nights and across instruments. For astronomers, such periodic brightness variations usually indicate rotation, because an uneven surface reflects different amounts of light as an object turns. In the case of 3At, a rotational period could indeed be inferred from the light curve, suggesting that 3At was spinning in a stable and measurable way. This alone would not have been unusual, because rotation is common among comets, asteroids, and interstellar debris. What made the signal from 3At distinctive was the presence of sharper brightness pulses superimposed on the broader rotational modulation. These pulses did not align cleanly with the expected rotation cycle of 3At, which meant they could not be explained simply by shape or surface albedo. Instead, the light curve of 3At appeared to carry two overlapping rhythms, one slow and continuous, and another intermittent and abrupt. This separation suggested that rotation provided a background tempo, while another process periodically injected energy or material into the surrounding environment. When the timing of the brightness pulses was compared with the episodic changes in the trajectory of 3At, the correspondence became difficult to overlook. Periods of enhanced brightness tended to cluster around the same intervals where non-gravitational accelerations were inferred, even though the measurements came from entirely different data sets. For 3At, light and motion seemed to speak the same temporal language. Such coupling between photometric behavior and orbital dynamics implies a shared physical origin, because unrelated processes rarely synchronize so consistently. If brightness pulses in 3@Last were driven by transient releases of material or energy, then those same events could plausibly generate thrust. This interpretation did not require intelligence or intention, but it did require an internal mechanism capable of operating in cycles rather than continuously. The rotation of 3@Last therefore became a reference frame rather than an explanation, providing context without resolving the anomaly. 3@Last rotated as expected, but within that rotation emerged a second rhythm that resisted simple classification. In this layered timing structure, 3@Last began to resemble a system governed by interacting processes, where rotation set the stage while episodic activity dictated the moments that mattered most. Beyond visible light, the behaviour of 3@Last extended into higher energy regimes, where observations in ultraviolet and X-ray wavelengths added another layer to the emerging pattern. Instruments designed to detect faint emissions recorded intermittent flashes from the region, surrounding 3@Last signals that could not be attributed to background radiation or instrumental artifacts. These emissions appeared sporadically, yet their timing showed a coherence that mirrored the brightness pulses already identified at optical wavelengths. X-ray emission from small bodies is not unprecedented because interactions between solar wind particles and neutral gas can produce faint X-ray signatures. Ultraviolet emission can also arise when energetic processes excite atoms and molecules in a surrounding coma. What distinguished 3@Last was not the presence of these emissions, but their structured recurrence and their alignment with other observed phenomena. When analysts compared the timing of X-ray and UV pulses with the photometric light curve of 3@Last, the correspondence revealed a shared cadence. Bursts of high-energy emission tended to coincide with increases in brightness and with inferred episodes of non-gravitational acceleration. For 3@Last, radiation, light and motion appeared to rise and fall together as though driven by the same internal clock. This level of synchronization is difficult to produce through independent processes because solar-wind interactions alone would be expected to vary smoothly with distance and orientation. Random fluctuations in the solar environment would not naturally align with discrete changes in trajectory or with repeating brightness pulses. The emissions from 3@Last therefore suggested that energy was being released in localized events, rather than through continuous exposure. One interpretation considered whether transient outbursts of material could temporarily increase the cross-section of 3@Last, enhancing its interaction with the solar wind and generating short-lived radiation. If such outbursts occurred episodically, they could explain why emissions appeared in bursts rather than as a steady glow. However, this explanation required that the timing of those outbursts be governed by a mechanism capable of repeating with consistency. As the dataset expanded, the alignment between X-ray, ultraviolet and optical behaviour grew harder to dismiss as coincidence. 3@Last was not emitting energy chaotically, but in patterns that suggested coordination across multiple physical domains. Whether this coordination arose from an exotic internal structure or from an unfamiliar interaction with the solar environment remained uncertain. What became clear was that 3@Last could no longer be described by a single observable, because each wavelength added a piece to a system that behaved as an integrated whole rather than as a collection of unrelated effects. The convergence of motion brightness and high-energy emission led researchers to consider whether 3@Last was governed by an internal mechanism capable of synchronizing multiple physical processes. Such a mechanism would not need to be complex or intentional, but it would need to operate repeatedly and influence mass release energy emission and momentum transfer at the same time. For 3@Last, the question shifted from identifying individual anomalies to understanding how those anomalies could remain phase-locked across different observational domains. One class of hypotheses focused on internal pressure cycles within 3@Last, where volatile materials beneath the surface could accumulate energy and release it intermittently. In this scenario, sublimation would not occur smoothly at the surface, but episodically beneath a semi-rigid layer that temporarily trapped gas. When structural limits were exceeded, 3@Last could vent material in short bursts, producing simultaneous brightening, radiation and thrust. Another possibility considered the layered composition of 3@Last, where different materials with distinct sublimation thresholds were distributed unevenly through the interior. As 3@Last rotated and its thermal environment evolved, specific layers could activate abruptly rather than gradually introducing a stepwise behaviour into otherwise continuous processes. This would allow 3At to display sharp transitions, even though the external heating changed slowly. However, these internal explanations carried their own constraints, because the timing of the pulses appeared more regular than many natural fracture or erosion processes would allow. For 3At to maintain synchronization over extended periods, internal conditions would need to reset reliably after each event. Such repeatability suggested a feedback loop rather than a one-time structural failure. Some models explored whether interactions between rotation and internal stress could create a resonance cycle, where mechanical strain built up and released in coordination with the spin of 3At. In this view, rotation would not cause the pulses directly but would regulate when internal thresholds were crossed. 3At would then behave like a system that periodically re-enters the same energetic state as it turns through space. None of these hypotheses required intelligence or guidance, yet none could be fully validated with the available data. Each proposal explained certain aspects of the behavior of 3At, while leaving others unresolved. What unified these ideas was the recognition that 3At could no longer be treated as a simple inert body. Instead, 3At increasingly appeared as a coupled system, where internal structure, rotation, and environment interacted to produce coordinated outcomes. Until that internal architecture could be observed directly or inferred more precisely, the synchronized behavior of 3At remained a hypothesis rather than a conclusion. Among the natural explanations considered for the early activity of 3At carbon dioxide sublimation emerged as the most conservative and scientifically grounded starting point. Carbon dioxide is far more volatile than water ice, meaning carbon dioxide can transition from solid to gas at much lower temperatures and at far greater distances from the Sun. For interstellar objects like 3At, this property provides a straightforward reason why visible activity could begin long before the object approached the inner solar system. Spectroscopic observations of 3At detected signatures consistent with carbon dioxide dominating the early outgassing process. This finding aligned well with the timing of the first observed coma, because water-driven comets typically remain dormant until they cross inside the orbit of Mars. 3At, by contrast, displayed activity while still far beyond that threshold, a behavior that carbon dioxide sublimation can naturally explain. From a modelling perspective, carbon dioxide offered an elegant solution to several initial questions. Carbon dioxide jets could account for the unexpected brightness of 3At at large heliocentric distances, and carbon dioxide outgassing could plausibly generate non-gravitational acceleration without requiring exotic physics. At this stage of analysis, 3At appeared to fit within an expanded but still familiar category of volatile-rich cometary bodies. Early simulations showed that if carbon dioxide ice were distributed unevenly across the surface of 3At localized jets could form and produce measurable thrust. Such jets would not need to be powerful in absolute terms, because even small forces can accumulate significant effects over interplanetary distances. In this framework, 3At remained a natural object whose unusual behavior stemmed from composition rather than from any fundamental departure from known physics. The carbon dioxide hypothesis also aligned with comparative studies of other distant comets, some of which show early activation driven by super-volatile compounds including carbon monoxide and carbon dioxide. By placing 3At within this broader context, researchers initially viewed its behavior as extreme but not unprecedented. 3At seemed to occupy the far end of a known spectrum rather than standing outside it entirely. At this point in the investigation, carbon dioxide served as a stabilizing explanation. The activity of 3At could be framed as an exaggerated version of familiar processes, allowing scientists to extend existing models rather than discard them. Yet even as carbon dioxide appeared to resolve the question of early activation, it quietly set the stage for deeper contradictions that would emerge once 3At passed its closest approach and the assumptions of thermal control began to unravel. As 3At moved past its closest approach to the Sun, expectations grounded in thermodynamics began to fail in a way that could not be ignored. In standard cometary behavior, activity peaks near perihelion and then declines steadily as the object recedes and solar heating diminishes. For 3At, the opposite trend emerged because signs of activity intensified after closest approach rather than fading away. Measurements taken weeks after the flyby showed that non-gravitational acceleration associated with 3At became more pronounced as the object moved outward. This inversion placed 3At in direct conflict with the basic assumption that sublimation strength tracks temperature in a smooth and monotonic way. If carbon dioxide sublimation were the sole driver, then the reduction in solar energy should have produced a corresponding reduction in thrust. Instead, 3-at last appeared to generate stronger and more frequent impulses during a period when thermal input was objectively decreasing. The timing of these impulses suggested that energy release was not responding directly to surface temperature but was delayed, redirected, or governed by another process entirely. For 3I Atlas, this reversal could not be resolved by minor adjustments to existing thermal models. One proposed explanation involved thermal lag, where heat absorbed during approach continued to migrate inward, even as the surface cooled. In principle, delayed heating could allow sublimation to persist beyond perihelion, but such a mechanism would still produce gradual changes rather than abrupt directional shifts. The observed behavior of 3I Atlas did not resemble a slow release of stored energy, but a sequence of distinct events. Another difficulty arose from the changing direction of the inferred thrust. If heating alone controlled outgassing, then the orientation of jets on 3 Atlas should remain tied to fixed surface features and rotation. Instead, the direction of acceleration shifted too rapidly to be explained by rotation alone, suggesting that 3 Atlas was not venting from stable, long-lived sources. This mismatch between thermal input and mechanical response forced a reassessment of the carbon dioxide framework. Carbon dioxide could explain why 3I Atlas became active early, but carbon dioxide alone could not explain why activity intensified when heating declined. The physics of sublimation does not naturally reverse its own gradient. As a result, researchers began to explore whether internal energy storage phase transitions or structural changes could decouple surface temperature from activity. Such mechanisms would imply that 3 Atlas possessed an internal architecture capable of regulating energy release independently of immediate solar conditions. At this stage, 3 Atlas no longer fit comfortably within the category of thermally driven bodies. The reversal of expected behavior marked a turning point in interpretation. What had begun as a compositional explanation evolved into a structural problem where the internal response of 3I Atlas appeared to dominate over external heating. This inversion did not identify a new mechanism, but it clearly demonstrated that the simplest thermodynamic narrative was no longer sufficient to describe how 3I Atlas was behaving. With thermal explanations, strained attention turned inward toward the possibility that 3I Atlas was storing and releasing energy through internal pressure, rather than responding directly to surface heating. In this view, volatile materials inside 3 Atlas could accumulate gas beneath a semi-rigid layer, allowing pressure to build until structural limits were reached. When that threshold was crossed, 3 Atlas would vent abruptly, producing a short-lived burst of material radiation and thrust before resetting the cycle. Such pressure-driven behavior is not unknown in planetary science because geysers on icy moons operate through similar principles, although under very different environmental conditions. For 3I Atlas, the challenge lay in sustaining this process repeatedly, without catastrophic failure because each release would impose mechanical stress on an already small structure. If 3I Atlas were capable of regulating pressure rather than simply rupturing, then its interior would need to possess both strength and resilience beyond that of typical cometary ice. This line of reasoning introduced the question of energy source, because pressure must ultimately be powered by something. Solar heating could contribute indirectly by driving sublimation at depth, but the timing of the observed event suggested that energy accumulation and release were not tightly coupled to immediate sunlight. 3 Atlas therefore appeared to act as an energy reservoir rather than a passive radiator. Some models explored whether phase changes between different states of volatile compounds could store latent energy inside 3 Atlas. Transitions between solid phases or between trapped and free gas states could potentially release energy in discrete steps rather than continuously. If such transitions occurred unevenly throughout the interior of 3I Atlas, then episodic behavior would emerge naturally from the structure itself. Another possibility involved mechanical stress generated by rotation, where centrifugal forces interacted with internal cavities or weak zones. As 3I Atlas spun, stress could accumulate until localized failure allowed material to escape, briefly altering both brightness and momentum. In this framework, rotation would not dictate timing precisely, but would modulate the conditions under which release became possible. What unified these internal models was their departure from surface-driven explanations. Each required 3 Atlas to possess an internal complexity that extended beyond simple porous ice and dust. Such complexity would help explain why 3At remained intact, despite repeated energetic events that should have fragmented a less coherent body. Yet none of these hypotheses could be confirmed directly because the interior of 3At remained hidden beneath its surrounding coma and dust. Without direct sampling or high-resolution imaging, internal pressure remained an inferred quantity rather than an observed one. 3At thus occupied an ambiguous category where the evidence pointed inward while the mechanism remained out of reach. At this stage, the behaviour of 3I could be described as energetically active without a clearly identified engine. The object was releasing energy in organised bursts, but the origin of that energy could not be traced to any single known process with confidence. In confronting this gap, scientists were forced to acknowledge that 3At might be operating under physical conditions not yet fully represented in existing models. Estimates of the physical size of 3At introduced one of the most persistent constraints on every proposed explanation, because size determines both capacity and limitation in small bodies. Based on brightness, thermal emission, and modelling of the surrounding dust, 3At was placed within a range of roughly 800 to 1,000 metres in diameter. For an interstellar object, this scale is unremarkable, placing 3At between much smaller debris and the larger nuclei of long-period comets. At this size, the surface area of 3I limits how much material can be exposed to sunlight at any given time. Even if volatile-rich regions dominate the exterior, the total energy absorbed from the Sun remains bounded by geometry. This creates a physical ceiling on how much gas 3I can produce through sublimation alone. When this limitation is applied to the observed behaviour of 3I, tension immediately arises. The measured non-gravitational acceleration implies thrust levels that approach the upper bounds of what an object of this size should be able to generate. For 3, Atlas to sustain repeated impulses strong enough to alter its trajectory measurably, the efficiency of mass-to-thrust conversion would need to be unusually high. Comparative studies of known comets reinforce this concern, because objects of similar or even larger size rarely display such persistent activity without rapid depletion. Small nuclei typically exhaust their most volatile components, quickly leading either to a decline in activity or to structural failure. 3At, however, showed no clear signs of exhaustion during the period of intensified behaviour. This discrepancy sharpened the size problem into a fundamental constraint rather than a minor uncertainty. If 3At were significantly larger than estimated, then the energy budget might become more plausible, but observational data did not support a dramatic underestimation. If 3At were truly within the measured range, then its performance exceeded expectations derived from standard cometary physics. The size of 3At therefore functioned as a limiting boundary that every hypothesis had to respect. Any mechanism proposed to explain the behaviour of 3At had to operate within the narrow margins imposed by mass surface area and structural integrity. As these margins tightened, it became increasingly difficult to reconcile the observed activity with the modest scale of the object itself. In this way, size transformed from a descriptive parameter into a central obstacle, because 3At appeared to be doing more than its dimension should reasonably allow. The question of energy budget followed naturally from size, because thrust is ultimately a measure of how efficiently energy is converted into motion. For 3At, the observed changes in velocity were small in absolute terms, yet significant enough to disrupt long-term predictions when integrated over time. Even a few meters per second applied intermittently accumulates into large positional offsets across millions of kilometers of travel. To generate such thrust, 3At must expel mass at sufficient speed, and that expulsion requires energy that can be traced to a physical source. In conventional comet models, solar heating provides that energy by driving sublimation, with the escaping gas acting as a natural reaction engine. For 3I, however, calculations showed that the implied thrust approached the upper edge of what solar input alone could reasonably supply. This imbalance became clearer when the timing of the thrust events was considered alongside heliocentric distance. As 3I moved away from the Sun, the available solar power declined, yet the inferred impulses did not weaken accordingly. Instead, the thrust associated with 3I appeared to remain strong, or even intensify during periods of reduced external energy input. Such behaviour strained the assumption that the energy budget of 3At was dominated by immediate solar absorption. If solar heating were the sole driver, then thrust magnitude should scale smoothly with distance declining as illumination decreased. The data suggested that 3-At was accessing stored or internally regulated energy, rather than responding directly to sunlight. This led to a deeper accounting problem because any internal energy reservoir must itself be filled by some process. Chemical energy phase transitions or mechanical stress could in principle store energy inside 3-At, but each option introduced efficiency limits. For 3-At to sustain repeated thrust events, energy would need to be stored, released and partially replenished without rapid degradation. The efficiency implied by the observations challenged existing models of small body energetics. Most objects of comparable size lose mass and energy quickly, when driven hard, leading to diminishing returns over time. 3-At did not display this expected decline, which suggested that either the energy conversion process was unusually efficient, or that the true budget had not been correctly identified. As a result, the thrust of 3-At could not be evaluated in isolation, because it exposed a mismatch between known energy sources and observed mechanical output. This mismatch did not point to a specific alternative explanation, but it clearly indicated that standard assumptions about how small interstellar bodies spend their energy were incomplete. Structural stability became the third pillar of the problem, because sustained activity places mechanical stress on any small body, especially one undergoing repeated energetic events. For 3-At, the persistence of its physical integrity stood in contrast to what has been observed in many comparably sized comets. When volatile release becomes intense, internal pressure and thermal gradients often lead to cracking, fragmentation, or complete disintegration. In known cases, small cometary nuclei subjected to strong outgassing frequently break apart, shedding fragments that alter brightness patterns and mass distribution. These breakups are visible in observational data as sudden changes in light curves, expanding debris fields, or multiple nuclei separating over time. 3-At, however, showed no such signatures even as its activity intensified. The absence of fragmentation implied that 3-At possessed a degree of cohesion not typically associated with loosely bound aggregates of ice and dust. To withstand repeated internal pressure, releases the structure of 3-At would need to distribute stress without catastrophic failure. This requirement pointed toward either an unusually strong internal matrix or a composition that behaved differently under thermal and mechanical load. One possibility considered was that 3-At contained a higher proportion of refractory material, providing reinforcement that limited cracking. Another option involved a layered interior where pressure could be vented through controlled pathways rather than through random rupture. In both cases, the structure of 3-At would act not as a fragile shell, but as a regulated system capable of surviving stress cycles. The challenge with these interpretations was that they demanded consistency across time. Structural resilience is not only about resisting a single event, but about surviving many without progressive weakening. For 3-At to remain intact, each episode of activity would need to leave the overall integrity largely unchanged. This persistence sharpened the trilemma because size, energy and structure could not be adjusted independently. A stronger structure would add mass-altering size estimates, while increased mass would change the energy required to produce observed accelerations. Yet observations constrained all three parameters simultaneously. As a result, structural stability did not resolve the mystery of 3-At, but intensified it. The object appeared too small to be this energetic, too energetic to be this stable, and too stable to behave like a typical comet. These contradictions did not imply impossibility, but they did suggest that 3-At occupied a narrow and unusual region of physical parameter space. In remaining whole while repeatedly altering its motion, 3-At challenged assumptions about how small interstellar bodies endure stress, leaving open the possibility that its internal makeup differed fundamentally from what has been observed before. A dense veil of dust surrounding 3-At introduced a new layer of complexity, because observation depends not only on what an object does, but on how clearly it can be seen. Spectral and photometric analyses indicated that the dust particles around 3-At were concentrated near a remarkably narrow size range of approximately 10 microns. This specific grain size is highly efficient at scattering sunlight, which meant that much of what telescopes detected was not the solid nucleus of 3-At, but the luminous cloud enveloping it. The presence of this dust veil altered the apparent position of 3-At in subtle but important ways. Astronomers typically locate small bodies by tracking the center of light, assuming that brightness is symmetrically distributed around the nucleus. For 3-At, that assumption became uncertain, because an asymmetric dust cloud could shift the brightness centroid away from the true center of mass. As a result, even precise measurements could carry systematic bias, introducing errors that propagate through orbital calculations. Each positional estimate of 3@Last relied on the previous one, meaning that small offsets could compound into larger uncertainties over time. This effect alone could widen the predicted trajectory region of 3@Last, contributing to the expanding cone of uncertainty. However, the dust veil of 3@Last could not fully explain the observed behaviour. Measurement errors caused by dust would be expected to introduce noise that fluctuates randomly, rather than producing consistent step-like changes. The deviations associated with 3@Last showed structure and timing that exceeded what observational bias alone could generate. The composition of the dust itself raised further questions because a narrow grain-size distribution suggests selectivity rather than chaotic fragmentation. In typical cometry activity, dust spans a wide range of sizes, reflecting violent and irregular breakage of surface material. 3@Last appeared to release dust in a more constrained way, hinting at an underlying process that favoured specific particles. This selective dust environment acted as both a mask and a signal. The veil obscured direct observation of the nucleus of 3@Last, complicating precise tracking. Yet the uniformity of the dust carried information about how material was being released. In this dual role, the dust surrounding 3@Last blurred the view, while simultaneously suggesting that the object's activity was governed by more than random erosion. One of the most visually striking features associated with 3@Last was the appearance of an anti-tail, a dust structure that seemed to extend toward the Sun rather than away from it. In most cometry contexts, such a feature is explained as a projection effect, where older dust trails align with the observer's line of sight and create the illusion of sunward motion. For 3@Last, however, the geometry required to sustain this explanation appeared unusually restrictive. The anti-tail associated with 3@Last displayed clarity and persistence that exceeded what would normally arise from simple viewing alignment. To maintain such a structure, the dust particles involved would need sufficient mass to resist radiation pressure, which rapidly pushes smaller grains outward. This constraint implied that 3@Last was releasing relatively heavy particles rather than a chaotic mixture of sizes. When this observation was combined with the 10-micron dust veil already identified around 3@Last, a pattern began to emerge. Both features pointed toward a narrow and selective range of particle sizes, suggesting that material release was not governed by random fragmentation. Instead, 3@Last appeared to favour specific physical conditions under which certain grains were liberated while others remained bound. Organised release does not require intention, but it does require structure. For 3@Last to consistently emit particles capable of forming an anti-tail, the internal or surface processes driving release would need to operate within defined constraints. Such constraints could arise from layered materials, pressure-regulated vents, or mechanical pathways that preferentially transport certain grains.